Hi everyone, today's lab exercise is about standing waves in a string. So first of all, let's try to define what is wave. Wave is just the propagation of a disturbance or energy in space in general. That's what wave is. And then what is a standing wave then? So, just like, you can read the theory. Then a standing wave is usually formed like, for instance, you send a wave has a vibration, for instance. A good example would be a string. You send when you plank a string, what will happen is the string will move up and down. That's literally you are creating some kind of disturbance, and then that disturbance is just moving in in an environment, in this particular case in this string. So what would happen is, like, for instance, if the string is tied on both sides somehow, what's going to happen is, like, as you can see in this drawing, then when you plank it, then the string is going to vibrate. That means the wave will be propagating in this direction. And then on the other end, if it is fixed, what will happen is that wave in the string is going to start to propagate backwards, and then there will be a certain kind of interference. Then, as you can see, the interference, as an example, in this example, you can literally see it in a string. So this can be seen in a laboratory setup. Of course, we're not going to do this physically, but that's what happens normally. You can just try to hold the string like very tight, and then somehow, like, you can plank it, and then you will literally see, like, just the string moving up and down, forming some kind of this kind of motion if you hold it on those two sides. So that's what a standing wave is like. So whenever you are forming a standing wave, what happens is, like, there is a wave moving in this direction, and there is a wave that is coming in this direction. The one that is coming in the opposite direction, this one is the reflection of the other one. So when that happens, what will happen is, like, you can see some kind of amplified kind of wave that is very much visible for your eyes. Okay, so mostly, like, this can be conducted in an experiment setup. Then the next thing that happens is, like, what kind of parameters do we really need to fulfill so that we can get a standing wave. Standing wave happens for a certain frequency, for a certain wavelength, and so on and so forth. So in today's particular exercise, what we're going to do is we're going to take a certain frequency, and then we are going to see, like, what kind of wavelength normally creates. It's just like a particular kind of standing wave. Okay, then before we go directly into the experiment, the first thing that you need to know is, like, every wave is characterized by a certain set of parameters. So in general, waves are characterized by a wavelength, usually represented by Greek letter lambda, a frequency of oscillation. That means the frequency of oscillation means, like, how many times does the wave complete oscillation per second, and it's measured in hertz. Wavelengths, of course, it's being a length dimension, then it's measured in meters. Its SI unit is meters. And then, of course, there is wavelength, the wave speed v, represented in meters per second. Okay, so in terms of an equation, this is how you can write a formula or the equation to find the speed of a wave. Speed of a wave can be found using lambda times frequency. Okay, but in today's experiment, what we are going to do is we are going to use a string. So in a string, so for instance, let's take this formula first one. Okay, so every equation or every wave can be represented by this equation. Okay, so the other equation that we need for today's experiment is, like, so for a string that is held tight. Okay, so for a string, what you can do is, like, you can find the speed of a wave in a string. Okay, that is only you make sure. So for speed of wave in a string, can be calculated as also v equals the square root of f divided by mu. Okay, so I'm going to explain this characteristic. So that means like the speed of a wave depends on, like, let's assume that like you have a string like this, and then you're tightening this string, and then the speed that is traveling in this string, it depends on the amount of tightness in the string. That means F normally represents the tension in the string, okay, and it's of course force and measured in Newton, and mu is known as the linear density of the string. Okay, so linear density means like how much does that string weigh per length. That means mass over length, and that means it's measured in kilogram per meter. Okay, so now if we can measure F and if we can measure mu, or the linear density, that means we can measure the speed. Okay, if we can measure the speed and if we can find the wavelength of the spring, I mean the wave, then we can determine frequency. Okay, so now let's go ahead and then like try to define what is wavelength. So the wavelength in a wave, as the wave propagates like in a wave, is calculated as from crest to crest. Okay, that means from crest to crest, that's what one wavelength or one lambda of a wave is. You like if this wave continues like this, and it, and considering that like the wave is not damped, that means like it doesn't slow in any way. That means in an undamped condition, wavelengths can also be from trough, that means the lowest part of the lowest part of the wave to the next lowest part of the wave. Okay, so it's either from crest to crest or from trough to trough. Okay, or in terms of nodes, like from one node to the third node, or from the third node to the fifth node, that kind of, you can also do that. Okay, this is what one wavelength can also be in a uniform kind of wave propagation. So in today's experiment, then what are we going to do, that you may ask? So what we're going to do in today's experiment, I'm going to show you right here. So we're going to do the following. So the first thing that we're going to do is we're going to combine the two equations for speed. Okay, so how does it work? We're going to do the following. So we will have use this. So what we have is like the speed of a wave v can be calculated as lambda times frequency. Okay, then we're going to measure lambda. Okay, and then we know that v in a string, since we are using a string, is equivalent to F, or tension, divided by mu. Okay, so what will happen here is like you have v, and then you have this. So if you are using this equation, okay, what will happen is like you can put in lambda will be equal to v over f. Okay, then what we're going to do is like we're going to take this v and then we're going to replace it here. By doing so, we're going to find the following. Then lambda, that's the wavelength of a certain wave, standing wave in particular, can be calculated as 1 over frequency, the square root of f over mu. Now, if we try to rewrite this equation like this, 1 over f, the square root of mu, I'm not changing anything, multiplied by square root of f. Okay, so what's going to happen in this particular situation, this equation is very similar to a linear equation. I mean, it's like this looks like more of a linear, just a linear simple mathematical equation that is represented by y is equivalent to m times x. That means if you take a set of lambda values and put them on the y-axis, and then if you take a set of corresponding f values or tension or force in the string, and then if you take a set of those points and then you put them like on a graph, okay, then what's going to happen is like you draw the best fit line for the graph, and then you find the slope of that graph. Okay, then automatically the slope of that graph is equivalent to this m, but that m means 1 over f the square root of mu. So from here, if someone asks you to find f, then or frequency will be equal to 1 over, take frequency to the other side of the equation and bring slope down here, multiplied by the square root of mu. Okay, so that means in today's experiment what we are trying to do is we are going to find a given frequency that creates a standing wave, okay, by using just simply this formula. So this is a main formula for you to find the frequency using experiment. Okay, and then of course, you know, like there was an f real value, right? So you have f experiment, this is from experiment, and then you will find the percent error. The percent error is going to be the absolute value of f, you know, real or given, minus f from slope divided by f given, multiply that by 100%, and then that will just simply give you the percent error in the experiment. So let's go ahead and then probably I will show you, like, you know, what kind of you know, simulation we are going to use for this particular lab, and how we are going to find lambdas and root f's. So the first thing that we are going to use is, like, we're going to use this. I'm going to put it in the link, okay, and in the description. So what would happen is, like, I'm going to give you this. So then now you're going to use this simulation, okay, for as an example. This is a very nice standing wave, just as an example, okay. So if you see here, right, if you see here, you may wonder, like, how you are going to calculate the wavelength. So in this particular case, it's, you are told that the distance from here to here is 4 meters. Okay, so the length of the string is already given. So what we're going to do is we're going to come here and then fill this. So the mass of the string, you don't need it. The total length of the string is given, so therefore that value will be 4. And mu, so mu for this particular experiment is this. It's already given. It's 3.2 times 10 to the power of minus 3. That means 0.0032, and as I mentioned it, its unit is kilogram per meter. Remember, don't use my values. I mean, this is an example that I'm doing it for you. I encourage you to do your own set of values. Okay, the length of the string between the vibrators to the pulley, you don't need this one as well, because we are going to just simply stick with this, and we are going to assume this is also a 4 meter otherwise. Okay, then now you're going to go ahead and then, like, what you will do is you're going to create different number of loops. Okay, So you don't need necessarily have to create those loops, because our setup is different. So I'm going to show you like probably a few of them. So what's going to happen is like I'm going to pause this, for instance, because this creates fantastic kind of standing wave. How you may claim that, like, how do I know if that is a standing wave? You will know when you create a standing wave, because the amplitudes are going to be really, really high. And the result, like, okay, this probably is a standing wave. The amplitude means like, how high those things are moving up and down. As I mentioned, it standing waves just don't happen randomly. They are going to happen at a specific, tension and at specific frequency. Okay, so therefore, don't change the frequency. The frequency is given already, 125. This is an example. Like, if you take a frequency, for instance, 100, then you have to keep that frequency throughout the experiment, because that frequency is your real value. So as an example, for me, my real value is 125. So what's going to happen is like my accepted frequency here is 125. I need to fill that out. And it's measured in hertz. That means per second. Okay. And now the computed frequency from the slope, this is how I'm going to find it. So what's going to happen is like I'm going to come here, and then I'm going to temporarily pause it so that I can count the number of loops. 1 loop, 2 loop, 3 loop, 4 loop, 5 loop, 6 loop, 7 loop, 8 loop. So I have 8 loops. That means here, what is the number of loop that I have? The number of loop that I have is 8. I'm just putting it in randomly. I mean, it's had it been in a classroom setup or something like that, I would follow this. But otherwise, it's not going to change much, because eventually, what's important is you are going to graph that. The mass suspended. You don't have a mass suspended here. Instead, you have the whole total force. In a lab setup, like, we usually put in small masses here until we get like that, high amplitude kind of wave. But in this particular case, the force is directly given. So therefore, you don't need to fill out anything on this column. Rather, what you're going to do is like, for instance, like here, sorry, my eighth loop is here, so I'm going to use this other way it is. That's fine. Then F8, then what is the force that I have? That means the tension that created 8 loops is here, which is 50 Newton. So therefore, I'm going to come here and write 50. Okay. So I don't need to find, what is the measure length and ln particular, like for my case. In all my scenarios, what I'm going to have is like that is just simply that's simply 4, but you don't need to. But rather, what you need to do is like you need to find the wavelengths. You may claim that, like, how am I going to find the wavelengths? To find the wavelengths, what you're going to use is like you can read the theory in there in the manual, but you can find lambda by just simply applying this formula. Lambda is going to be equal to 2 times L. You're going to use L constant throughout this experiment, divided by n. Okay, so how much would that value be? So keep in mind, you're going to use this. Lambda is going to be equal to 2L divided by n. So 2L, what's going to happen to L? To L means 2 times 4. Okay, sometimes divided by n. N is the number of loops that you have here, which is 8 in this particular case, so therefore 8. Then you divide that, and 2 times 4 is 8. 8 divided by 8 is and of course that is going to be 1, right? So your wavelength here is 1. So, and it's measured in meters. Keep everything in SI unit. And of course, we already said this is 50. Then this value is going to be the square root of 50. Square root of 50. So, you can just approximate it like the way you may get it. Like this is going to be approximately 7 point something, 7.0 something. So you put your value here, and then now, okay, I just showed you one example. Like how you can find like square root of f, and I mentioned it. If you find a set of f values and a set of lambda values, then you can just simply plot the graph square root of f divided by, lambda versus square root of f on the graph. So I'm going to go ahead and then, like, for instance, just for the sake of it, I'm going to try to show you, like, okay, I'm going to go ahead and then, like, probably I'm going to change the force. The only thing that you can change in this experiment once you started it, like, first at the beginning you set your frequency. I already set my frequency here. And then second, set your mu value. I already set my mu value. And then third thing is, like, once you set those values, you cannot change those values at the middle of the experiment. The only value that you have to change is like f. So now I'm going to go ahead and then see, when I increase f, is it giving me a standing wave? No, because a standing wave only happens at a particular force, at a particular tension. It's not like some kind of a random kind of thing, okay? So I keep on increasing. You see, now I can literally see that, like, the amplitude, changes and starts to increase. So I keep on increasing until I see, like, an amplified kind of amplitude. Now this creates a very nice standing wave. You can see that. So therefore, approximately at a tension of 65, I was able to create another standing wave. Then I'm going to come and count how many loops I have. 1, 2, 3, 4, 5, 6, 7. So I have 7 loops. So for 7 loops I was able to create. So now my 7 is here. 7 loops was created at a force of 65 Newton. Then how much would be your lambda? Your lambda is going to be 2 times 4. Again, don't ask me where I found 4. 4 came from the length of the string. Literally the length of the string is that much. Then divide that by the number of the loops. So I have 7 of them. Okay, so 2 times 4 is 8. 8 divided by 7, then you're going to put that value right here. And then this value is going to be the square root of 65. That's going to be approximately approximately 8.0 something. Just put it in your calculator and then find it. I'm just simply using without a calculation. Okay, so you already know, like, what to find and what to do. So in particular, just like 7, and then one more I'm going to do. That is, like, let me try to I don't know, increase maybe the force, and then so that it's going to give me maybe a 6. Look, as I mentioned, that standing wave only happens in a particular force. It doesn't happen at 70. It doesn't happen at 71. It doesn't happen 75. At least for this example, it's not happening anywhere close to 80. So we'll just keep on increasing. Now I can see that, like, it's the string starts to form a wave, and then I will just slightly increase it. Lovely. That is good. So at about 88.75, I was able to create a loop, and then I will count the loops. 1, 2, 3, 4, 5, 6 loops. I was able to create 6 loops So the 6 loops was created at a force of 88.775. Okay, so try to collect like about at least five points, 5 data points. I expect you to collect at least 5 or 6 data points just for this experiment. Then you find the wavelengths. Again, the wavelengths is simply 2 times 4 divided by the number of loops that you created. In this particular case, it's about it's 6. So 8 divided by 6 is it's approximately 1.33, right? Okay, 1.33. And then of course the square root of your force is going to be the square root of the square root of 88, right? 0.75. So we have already investigated, and you already know how to graph things. Then the next item is going to be, once you collect 5 or 6 points, and then what you will be expected to do is you need to put your lambda values. Your lambda values are, those are your lambda values. Those are your lambda values, and then you put in your square root of f values on the x-axis. You know, if you can do it in Excel, that would be even easier. But otherwise, it's you can also do it on a graph paper as you always do, and then you find those values, those set of values, and then you graph it. Most likely, your graph is going to be a linear line. You draw the best fit line, you find the slope of that, then you put your slope over here, then your slope value has to be inserted in here. And then using that slope, what do? You need to find the frequency. How do you find that frequency? I already mentioned it, I already showed you in my whiteboard. Okay, so this is how you find the frequency. Okay, so this is where your frequency calculation will be done. Okay, so frequency equals 1 over the slope. You already found it from the graph, and then of course you are going to use the square root of mu. Your mu value is already determined from the simulation, right? And that mu value is this. So once again, make sure that like the only varying thing in your experiment is going to be, so this is how you are going to proceed. Set your f value, your f given, okay, before you start the experiment, and then you set your mu value, okay. Then once you start working on this experiment, and then of course you set your L value, which is 4, that's what it. So then what do you need to vary? The only thing that you need to vary is t. As you change the value of t, what changes? Then lambda will change. Okay, so this is how you are going to proceed. Then as always, write your report that following a proper format. So go to your Blackboard to see the format of the lab report that we normally use. Okay, bye.